Haha, there you go. This is take two. Morning, gentlemen. Morning, fellow teachers. Hello, I'm here to talk to you about heat treatment of metals to make them stronger, in particular steel. Now, steel is a compound. It's made up of iron, Fe, and carbon. Okay, so when you combine two or more elements chemically, you have a compound, and in this case, it's steel. Today we're going to look at a heat treatment process where before I became a teacher, I used to be an engineer and I used to do this as a living. That's right, what you are about to do today in the science lab, I used to do in the factory. Okay, so here we have, first of all, we need to talk about language. And when it comes to properties of metals, we've looked at the flame test. We know that when you excite the electrons, they jump shells, and then when they come back, they give off this special light. And different metals give off different colors, as you find out in the fireworks. We also looked at the conductivity of metals, whether they be as an element or as a compound, either crystal or in solution. And now we're looking at the properties of metals as far as their strength. And in particular, we are going to use the three words brittle, malleable, and ductile. So first of all, let's have a look at the word brittle. I always think of teddy bear biscuits. Remember the old teddy bear biscuits? You go and you go snap. That's right, that's brittle. So easy to snap. There you go. So brittle is things like, but you can do the same with metal, and you will discover that. Yes, today you're going to be able to snap metal. Wow. So the adjective you're going to use is a technical scientific term called brittle. The next one is malleable. Double L, able, and M. There's a male in there too, actually. Okay, malleable, I'm going to use this. Aluminium foil, made up of only one element. Which one on the periodic table? I always remember this one, the 13. There you are, aluminium, pure element, only one type of that. And what does malleable mean? I can bend it into or change its shape. That's what malleable is. So there you go, malleable. Now, ductile, unfortunately, I have not got an example of ductile. What happened to my ductile plasticine? I've got technical. Here my assistant's going to deliver me with some. All right, so I haven't got a metal, but what I do have, something to demonstrate what ductile means. You're able to stretch it. And we are able to take metal and stretch it. We used to have to take metals that we got, which was in a soft state, and we were able to stretch it so we could make the screw part. We would make the screw. That's right, the bottom part of the screw, and we would change its shape to malleable by making the head of the screw, and of course we would make the tips. So we wanted a material that was both ductile and malleable. Okay, stretch it and change its shape. However, when we went to sell it to the customers, they say, hey, we can't screw into this metal. It needs to be strong. So that's what we did. We used to do what's called a heat treating process. And during this heat treating process, we actually experienced all three qualities. So let's have a look at the heat treatment process. There are three. And guess what? You're going to be able to do this in the class, in the science lab. I used to do it in a big factory. For this, we needed a big furnace, an oven. It was the size of this room, your lab. And inside, at the start, we put the screws in, about your weight in screws. Imagine your weight converted into screws. We would stick it in here, and it would go through this oven at a very special temperature, 900 degrees Celsius. Now you must probably be wondering, where am I going to find 900 degrees Celsius? That's why we invented the Bunsen Burner. Well, we didn't invent the Bunsen Burner. Here's where we quickly draw a Bunsen Burner. Make sure, nice and simple. And we have two parts of the flame. Remember, there's a blue flame We want not the safety flame, the blue flame. And when you do, you carefully look, you'll actually see there's two cones, an outer cone and an inner cone. And it's the inner cone that gives us 900 degrees Celsius. So yeah, we're going to be able to reproduce it in the lab. So we're going to heat it up so it becomes red hot. We used to have a little window, I could see inside there. We used to go red hot. We actually even had special gas in there, ammonia gas, which almost killed me. That's why I got out of it and became a teacher. It's much safer. Right, so it comes out at 900. When it came out, we had two options. It could just go and sit there, or it could go into a special bath. Well, it was a special bath made out of oil. Now, you're not going to use oil, you're going to use water. Okay? You're going to use water instead. And finally, once we took it out of there, we would then take it to another special oven. But this oven was circular, and we would lower the screws in there, put a big lid on it like a pressure cooker, and we would leave it in there for 45 minutes at a special temperature, 400 degrees Celsius. Now, where are we going to find? Can anyone guess where we're going to find the 400 degrees Celsius? So we had 900 here at the inner tip. That's right. We have 400 degrees Celsius at the top tip. So, let's go through the process of annealing. Remember, you will have 4 of these. Okay? The first one, you do nothing to it. That's no treatment. The second one, you're going to do what's called annealing. Here we go. You're going to put it through 900 degrees Celsius, but by putting it in the tip of the inner, the middle part only. And you have to make it yellow hot. It will turn yellow hot. As soon as you take it out, we need you to place it on the cement sheet so it can be air-cooled. Air-cooled. So annealing is 900 degrees Celsius, yellow hot, and air-cooled. And you put that aside next to that. Don't mix them up. You get the next one. There you go, the next one. This time we're going to do the quenching. Oh, that's like quenching your thirst. We have to cool it down much more quickly, like, I'm hot, I need some water, quenching. So we, again, 900 degrees Celsius. So we used to put some screws, we put them through here, and then we quickly dump them in the oil, but you're not going to use oil, you're going to need water. We didn't use water because it would evaporate. All right, so we're doing yellow again, yellow hot in the middle, and we're doing water cooling. Oh, you're going to be introduced to chemical formulas, H2O. That's a little 2, by the way. And put that aside. So you now have no treatment, normal annealing or normalizing, and the last one was quenching. And the final one was this one here, tempering. Now, tempering meant that we had to do 2 processes. 2 processes. We had to go through this process here. We had to go through into quenching, and then we had to put it in here to finish off the process called tempering. And as our company was interested in making metals that were strong, because we needed to screw them into other roofing, so they had to be strong. They couldn't be brittle, and they couldn't be malleable. Yes, we needed to be malleable so that we could change its shape. We needed to be ductile so we could change it so it's long screws, but we then had to turn it into very strong. Not hard, we didn't want it to be brittle, we don't want it to smash or crunch or crack, we need to be strong. So we went through this process. So you're going to heat it up to 900 degrees, so quickly dump it in. Then, guess what? When I came to Mazenod College, I was absolutely gobsmacked. I thought, my God, look at that colour. Yes, this is the colour that I used to watch every day. When those screws came out of the tub, they were this colour teal. And we knew we got it right when we just looked at the colour. So yes, that's what you're going to look for. So you're going to get the fourth piece. You're going to heat it up, right, 90 degrees Celsius, dump it in the water, come out. Oh, let's take that plastic coating off because we need to see that color. And now, with your tongs, don't forget, read your apparatus, read your method. There you go. We're heating up again the same area that we heated up the first time. But this time, we're doing it gently. Don't make it yellow or red hot. You just want to gently heat it. Even maybe rotate it like a chicken or a pig. Okay, so we're gently heating up in the 400. Where's that? Yes, there it is right there. The Bunsen Burner has the 400 at the top tip. So we're using it there. So you're just going to put it there. Oh, check with your tire. Check with your tire. Oh, no, a little bit more. A little bit more. And there you go. So we have now got our treatment. Now, by the way, independent, dependent, and control variable. Let's talk about that. Here we have. What did we change? Remember, the independent variable is what you control, what you change. What did we change? We changed the type of treatment. What is the dependent variable? Oh, that's right. When I record something, what are we recording? The number of bends. That's what we're recording, and we can see if there's a pattern. I won't let you see that. You'll do that further. That's your aim, to see if you can come up with valid and reasonable results. So now we're ready to do the bend test. Okay, this is when you use it, not for heating. Remember, there it is. Remember, it's the middle part that got heated up. Go to one side of the middle part, still there, the middle part right next to it. Grip it. Hang on. What's the control variable? Something that you want to be consistent, that doesn't change. Guess who that is? Me, yes. Only one person in your group will know how to consistently bend this properly. So make sure they grip it hard. You don't want a sloppy grip. You don't want it to move in that grip. You want to be a strong grip. Ready. This is no treatment. Now, I'm going to count one bend. You're doing Pythagoras' theorem, aren't you, in maths? That's 90 degrees. So let's go. 90 degrees. One bend. That's one bend. We're going to take it back to where we started. That's another bend. That's two. We go the other way. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Gee, that's very what? Which word would you use? Brittle, malleable, or ductile? I don't know. You all get different results there. Again, you then take the one that was annealing. Same process. Make sure record your result. Then you do the one that was quenched. Okay? All right. Do that one. And finally, this last one, which was the tempering. The one that I believe makes things strong. Do we want it to be malleable? No. Do we want it to be brittle? No. We want it to be strong. So hopefully you'll be able to make the connection. All right? And when you see the results, and maybe your classroom results as a group, you'll be able to see those that did the job well, especially the tempering. You'll know you've done well when you can get a combination of both strong and... However, we have got no way of measuring it strong. See, back in there, we used to do drill tests, see how long they took to drill through the metal. And usually take maybe 2 seconds, 1.5 seconds, but we can't do that today. So I hope that will help you, and don't forget your teacher, ask them. I'm sure they'll be able to help you with the conduct of this. And think about it. We were able to reproduce a process in a major factory in the science lab. And so hopefully you'll be able to see the connection between science, engineering, and the every day-to-day product that you see out there that's being used. So actually I think all on the fences, those teal fences, have a look at the screws. I'm telling you now, it's got the letters BX. That's Buildex. That's who I used to work for. Have a good day.